So, welcome my friends, welcome to my next lecture. So, this lecture I have a plan to talk about what is called iterated integrals, right. That the notion of double integral or so Riemann Darboux integral that I have discussed, like using two ways you can define it. One is like upper sum, lower sum and upper integral, lower integral, and whenever they are equal. Another way to approach or to define it in terms of Riemann sum. So, I have discussed those part in my last lecture. Now, this lecture I will talk about the notions of iterated integrals, then it will come like what is called Fubini's theorem that will tell you that when iterated integral and double integrals they are equal, and then I will talk about change of variable formula in a double integral, and if time permits then I will talk about some applications of integral in like to calculate the volume and areas. Okay. So, as I said, I should start with the notion of iterated integrals. Okay. So, the notion of double integral or Riemann Darboux integral I have discussed in my last lecture in terms of Riemann sum or in terms of upper integral and lower integral. So, now what is iterated integrals? Like as I said, iterated limits, you know, like if I have a functions from say R2 to R, then there is a notions of iterated limits. That means iterated means what? That means if I have a functions of two variables, say that is functions from R2 to R, then you keep one variable fixed, say either x or y. If think about is a function of single variable and perform the limit. So, if I fixed x variable fixed, then perform the limit for each fixed x, it will give you a value, and then you perform the limit in terms of x. So, that is called iterated limit. Similarly, iterated integrals also similar kind of thing. So, that means you have to fix one variable, think about the functions as a single variable in the other one, and perform the integrations, and for each x it will give you some value, and then this you can think about as a function of x and make a integrable or Riemann integrable or Riemann integrable in the single variable case. As you know, you perform that one, that is called the iterated integral. So, let me see what I have done. So, let f be a functions from some set R which is subset of R2 okay, to R. Suppose that what I am doing again, see I am fixing an x in the interval a b. So, that means I should say that what is my R? It is the bounded square region, that means a cross b times c cross d. In my next slide I have written explicitly. Okay. So, what I am doing is that I am fixing an x from closed interval a to b. I fixed x. For the fixed x, I am considering the functions y goes to f of x y for fixed x. Fixed x is in closed interval a b. So, now if I fix x, I can think about a functions from y goes to f of x y and y is running from c to d. So, now I have a function single variable functions defined on the interval closed interval c to d, 2 belongs to R. Now, if that I can integrate, suppose this function is integrable. So, that is exactly I have written. I am integrating c to d of this function, that means f of x y dy, keeping x variable fixed. And suppose integration makes sense and suppose integral exists, then it will give you some real number. So, I am denoting as a functions phi of x. So, that means for each x I am integrating my functions y goes to f of x comma y over the interval c to d. It will give you a point or it will give a number, and then I am associating that for each x phi x is that number. So, that is in nothing but this one. So, therefore, phi is a functions. So, suppose this integral as I have written, let f subset of this, suppose that for each x phi x exists. If phi is Riemann, now phi is a functions, right? Phi is a function from where to where? X is running from closed interval a b. So, phi is a functions from a b to r, right. So, now since phi x exists for each x in the closed interval a b, so therefore, the functions I can talk about whether it is Riemann integrable on my closed interval a b or not. Now, the assumption I say that if phi is Riemann integrable on closed interval a b, then of course, the integration a to b phi x dx makes sense, integration a to b phi x dx makes sense. And what is that? This is nothing but integration a to b, we just replace phi x because phi x is here. So, that means this is nothing but integration c to d f of x y dy, and then you have an integration with respect to x. It's clear? So, therefore, start with the functions f from say bounded rectangular region to R, fix x from closed interval a b, define that function y goes to f of x y on the interval c to d. Suppose it is that function is integrable over the interval c to d, then it will give you a functions phi of x for each fixed x. Now, if the functions phi is integrable on the interval closed interval a b, then I can have right integration a to b phi x dx, which is nothing but integration a to b then integration c to d f of x y dy. So, here actually what? Keeping x is fixed, I am integrating with respect to y, it will give you a function of x, and then I am integrating with respect to x. If these things happen, then I will say that this is iterated integral of f over the region R. Now you may ask the same questions like, okay, instead of fixing x, if I fix first y and then define a function psi of y, and if I assume that psi is integrable, then I will have another way. Yes, answer is correct. So look, similarly I have written, so what you are doing in this time you are keeping this is fixed, right. So y is fixed. For each fixed y, you consider the function x goes to f of xy, okay, over the interval a b, right. Suppose this function is integrable, in other words, suppose integration a to b f of xy dx, this is exist, you define this as a function of psi of y, and if psi is integrable, then this is again I will say that iterated integral of f over R. So that means I have given a function f from some rectangular bounded rectangular region subset of R2 to R, it will give you two iterated integrals. So first one is that you are keeping the x variable fixed, integrate with respect to y, it will give you a function of x, and then do the integration over x variable. Second one, keeping the y variable fixed, think about is a function of x variable, do the integrations, and it will give you a function of y, and then perform the y integral. So this way these are two iterated integral exist for the given functions f on bounded square region. Okay, these are called iterated integrals. So this parenthesis, actually that first bracket, that means you just by looking at this dy, that means it is clear from the context that fix the variable x is fixed, perform the integration with respect to y, then it will give you a function of x, and then perform the integration with respect to x. Similarly here dx is here, then it is clear I am fixing my y variable fixed, perform the integration with respect to x, it will give you a function of y, and then perform the integration with respect to y variable. Of course, provided that integral makes sense, okay, integral exists. Okay, so as I said, I have just again explicitly written, so let f be a functions from R subset of R2 to R bounded region. So this is my bounded region, that means you have the region A, B cross C to D, okay. The following integrals, that means again I am just integrating, keeping x variable fixed, integrating with respect to y, and then perform the integration with respect to x variable. Here I am keeping y variable fixed, perform the integration with respect to x, then it will give you a function of y, and then I am performing with respect to the variable y. So these are called the iterated integrals over f, and double integral, the one I have explained, that means in terms of partition, in terms of upper sum, lower sum, or upper integral, lower integral, or in terms of Riemann sums. That means if it is defined on a bounded rectangular region, you take the partitions, you make a Riemann sum, and suppose you take a finer partitions, or say that norm of the partition goes to 0, if it exists it will give some limit L, and that L is nothing but the double integral of f over the region R, and I am denoting is this way. Now I have written, we drop the brackets or parentheses for the iterated integrals because it is quite clear, right. So whenever you just look at this with respect to what dy or dx is there, and then you can easily kind of guess that if it is dy means I am keeping x variable fixed and performing the integral over y variable, and then it will give you a function of x, and then I perform the integral with respect to x variable, and similarly here. So therefore there is no point of putting that parenthesis first bracket. Well, you can put it, that's not an harm, but my point is that just whenever I will write this way, it's automatically clear from the context that which one you have to keep fixed and with respect to what variable you have to perform the integration. Okay, now as I said, Fubini's theorem, it tells you some connections with the iterated integrals and double integrals. So what it says, so this is the statement of Fubini's theorem. So let f is defined from some bounded rectangle subset of R2 to R, this is your rectangle, okay. What is the statement? It says that if f is continuous functions on R. Now you see I already discussed in my last lecture, if my function is continuous, then my function is Riemann double integrable, that means double integral exists. If f is continuous, then double integral of f over R exists. Not only that, if since my function is continuous, so therefore if I fix one variable x is fixed, if I think about this function y goes to f of xy or x goes to f of xy, so this is means what function xy, that means I am keeping this is x is fixed and this is y is fixed. Okay. So now continuity of f will tell you the continuity of this single variable functions. So therefore this is also integrable, this is also integrable. So therefore both the iterated integral of f also exist, and what will happen, conclusion is that double integral, that means the Riemann double integral is same as the both iterated integrals. That means it doesn't matter. That means I can just perform the integration with respect to y variable first and then perform x variable, or perform x variable first and then y variable. But provided it is very important to notice or note that the function is continuous. So, continuity is a very strong assumption. So, continuity implies the double integral exists, or also iterated integral exists. Along with that, the value of the double integral is same as the value of the iterated integrals. So, that is called Fubini's theorem. So, in fact, this theorem has a good application. For example, if I give you some function and some region, say rectangular region, I say that okay, calculate the value of the double integral. So, now how do you calculate it? Now, that Fubini's theorem says that the double integral is nothing but one of the iterated integral, and you just perform the iterated integral. And iterated integral, that means what? That means you are keeping one variable fixed. Think about it is a function of single variable, and single variable integration, you know there are a couple of formulas, or you know how to do the integrations. If you do that, then you will be able to compute the what is called double integral. So, this theorem, Fubini's theorem, somehow helps us to calculate the double integral in terms of calculating the iterated integrals, because sometimes computing iterated integral will be easy rather than the double integral. Okay. So, that is exactly I have written. The above theorem gives a method to evaluate the double integral of f through evaluations of the iterated integrals. So, that means I want to evaluate double integral, rather I am evaluating it directly by the definitions. I use the iterated integral, that means keeping one variable fixed. Think about it as a function of single variable, and I know how to calculate the single variable Riemann integral, and then you can calculate it. So, that is one of the way to evaluate double integral. I will discuss one example, then it will be more clear. Okay. So, this is another version of Fubini's theorem. Earlier I have assumed the continuity, but you see a little bit relaxed condition is there. What is that? So, let f be a function from R to R. Again, R is the what is called bounded rectangular region. Okay. So, I have assumption is the following. What I am doing is that for each fixed y in the interval c to d, I am considering the functions f y, f suffix y, that means keeping y variable fixed, the functions f of x y, here x is varies. So, for each y I am having the functions f capital F suffix y. Now, if capital F suffix y, it is a function again, right, it is a function of single variable. So, it is a function from closed interval a b to r, because for each y fix c to d, now x is varies from where? Closed interval a to b. So, therefore, for each y capital F suffix y is a function from closed interval a b to r. So, what I am saying is that you fixed y in the interval c to d, consider the functions capital F suffix y, it is a function from closed interval a b to r. Suppose it is integrable over the interval a to b for each y. So, this is very assumption, strong assumption, right. So, that means I am keeping y variable fixed, I am writing for each fixed y a functions capital F suffix y, which is nothing but f of x y, where y is fixed, x varies on the closed interval a b, and I assume that for each y my capital F suffix y, these functions over the interval closed interval a b, it is actually integrable. If this is the case, then since of course f is integrable, double integrable I assume, let f be an integrable functions, then your double integral is exactly equal to the your what is called iterated integral. That means this is the iterated integral, right. So, that means you have to first performing the integration with respect to x variable keeping y fixed, and that is exactly the assumption is here, and then you can also perform the integration with respect to y variables second, and it is give you the value of your double integral. So, therefore, this is one of the kind of statement of another, I should say, another version of Fubini's theorem. So, what I want is that okay, keep y in the interval c to d fixed, associate y with a functions capital F suffix y, it is a functions from closed interval a b to r, and I assume that for each y capital F suffix y is integrable, and if it is the case, then your double integral, which is nothing but this one, is exactly equal to the corresponding iterated integral. First you have to fix with respect to x variable keeping y variable fixed, and then perform the y integrable. Similar kind of things will happen in the next statement. Instead of keeping y variable fixed, if I keep x variable fixed, right, that is exactly I have done for each x in the closed interval a b. Now, you fix x in the closed interval a b, and then you associate. So, that means x associate with f suffix x. Again, it is a functions from closed interval c to d to r, and what kind of functions? F x suffix acting on y, which is nothing but f x y. Okay. So, this suffix means this is fixed, y varies but the interval c to d. Again, what will be my assumption? My assumption is that for each x the functions capital F suffix x is integrable. Okay. So, if it is the case, then again your double integral is exactly equal to your iterated integral. That means, you first perform keeping x variable fixed, you perform the integral over y variable and then perform the integral over with respect to x variable. So, these two are statements, or this is little bit weaker version, because earlier I assumed that continuity, but this time I assume something different, that is for each y capital F suffix y is integrable and for each x capital F suffix integrable. If this is the case, along with the integrability of double integrability of f, it will tells you that your double integral exactly equal to your what is called iterated integral. So, Fubini's theorem gives a connections between double integral and iterated integral. Okay, as I said, so if I give some example, it will be more clear. See, look, example, evaluating the iterated integrals. Okay, so what to do? Okay, so let f be a functions f of x y, which is x square times y. Again, your region is very nice, it is a bounded square region, not square, rectangular region. Okay, so then you have to compute, suppose this double integral. Now, you know that since my function is continuous, you have a bounded rectangular region, then by Fubini's theorem says that the value of the double integral exists, value of the double integral. Of course, since my function is continuous, double integral, iterated integral all exist, and the value of the double integral is nothing but one of the iterated integral. You perform it, one of the iterated integral. So, for example, I am just doing the first one, that means keeping the x variable fixed, performing with y and then x. So, what will happen? So, this is means if I do integration with respect to y variable, keeping x fixed, that means x will come out, right, this x square will come out. So, only have this integration 0 to 2 y dy, and then you can easily calculate it. This is y square by 2, take the value y from 0 to 2 and then x square will be there, you have this one definite integral. So, the value will be 6, very simple. Okay. Now, you may say that okay, one of the iterated integral it gives, but it should be other iterated integral also should give the value of the double integral, and let's see whether these two values are same or not. Of course, it should be same, because I assume my function is continuous and Fubini's theorem tells you yes, both iterated integral exist and they will be same. So, just for curiosity, if you do that, okay. So, look, now this time I am integrating with respect to x variable, keeping y fixed. So, therefore, y will come out from the integral. You perform this integral x square dx, x from minus 1 to 2, and this should be x cube by 3. You can evaluate from minus 1 to 2, just perform this again y variable integration, definite integration, it will be 6. So, you see this is, so this is one of the way using Fubini's theorem to calculate double integral by performing evaluating iterated integrals. So, that is the case. Okay. So, now till now I have discussed what is called notions of double integral or iterated integral on a region which is bounded square region. Now, you may ask, okay, if I have a region which is not like bounded square region, maybe some bounded region, then how can I have the notions of the Riemann-Darboux integral over that region? And on top of that, what will be the corresponding notions of iterated integrals. So, that is what I have written. So, we have learned double integral over rectangular region, that I have already explained, okay, meaning of double integral and the meaning of iterated integral, then Fubini's theorem tells you the connections. Now, we will learn about double integral over simple and bounded region, which is not like what is called bounded rectangular region, but it is some bounded region which is also simple. I will explain a couple of examples. Okay. Then the question is, what will be the double integral in that case if R is a bounded region in R2? Then what is the double integral of f if R is over a simple region? I will talk about what do I mean by simple region. Okay. Then what will be the notions of iterated integral and Fubini's theorem in that setting of simple regions, and then I will talk about some applications and change of variables for this double integral, like polar coordinates and general transformation. Let me see, if I have a like say bounded region or simple bounded region, then how I can define the Riemann-Darboux integral or double integral in that setting. Okay, let us see. Okay. So, look, so what I have written, double integral of f over non-rectangular region. So, rectangular region I have already discussed how to make sense of a double integral. Now, what I am saying is that let D be a bounded region in R2, let f be a bounded functions and say real value on your domain D. Now, what I am doing is that, so if I have a bounded region, then arbitrary, it need not be a rectangular, right. So, what I am doing is that take a rectangular region R which actually contains your bounded region. That means, what I am trying to say is that, suppose you have a this R2, suppose this is your region, okay, suppose this is my D. So, what I am doing is that I am taking a square or rectangle, not square, some rectangle which actually contains your bounded region D. So, this is my R. So, this rectangular region it is actually R. And that is possible. Why? Because of my D is bounded. So, therefore, I can always have a rectangular region which contains my D. So, this is always possible because your region D is bounded. Then what I will do? Then I will define a function f2 del on the square region R that I have just obtained, or I have just made a square region which contains my bounded region D. What I am doing is that define a function f2 del which is from this square region or rectangular region to R. Okay, not square, I should say rectangular, that is very important. So, if I have a rectangular region R, that means what I am doing is that I am saying that okay, f2 del of xy which is exactly equal to your function f of xy as long as your xy is in the set D and outside it should be 0. Okay. So, what I am doing? So, that means I have a function, I have a domain, suppose it is a bounded region. Since it is bounded, then I can always find a rectangular region which contains my domain D. Then I am defining a function, new functions, what is called f2 del, and how I am defining? f2 del is nothing but f as long as your point xy is coming from D. So, that means in this region it is actually coincide with your D, and this region it becomes a 0. If I define this one, now you will have f2 del functions f2 del which is defined on a bounded rectangular region, and I already discussed if I have a functions bounded functions which is defined on a bounded rectangular region, then what is the notions of what is called Riemann-Darboux integral or Riemann integral or double integral. So, therefore, it makes sense because I have a bounded rectangular region. So, then I am saying that if the double integral of f2 del over the rectangular region R exists, and you know the notions I already discussed. If I have a bounded functions on a bounded rectangular region, then what is the notions of double integral? Suppose the double integral of f2 del on the rectangular region exists, then the double integral of f over your bounded region that you would like to investigate, I would like to give a meaning on the region D is defined by, how I define? Integral over the region, bounded region D of your function, that is the notation which is same as, is nothing but the integral of your newly defined function f2 del over the bounded rectangular region, and that you know, right, that you know from the earlier lectures. You know, if I have a bounded functions on a bounded rectangular region, then what will be the notions of double integral. So, that means what I am doing? So, I am starting to give a meaning of a double integral of my functions, nice functions, say bounded functions on some bounded region. What I am doing, since my region is bounded, I am first getting, or I am finding an rectangular bounded rectangular region which should contains my domain D, and which is possible because my D is bounded domain. Okay. Then what I am doing? I am defining a new function f2 del which is exactly equal to f as long as my point xy is in the set D, and if it is outside the set D, but still it is in the rectangular region, that means this kind of points it is taking the value 0. Now, I am saying that if my functions newly defined function f2 del defined on bounded rectangular region, and I know the notions of double integral, if that integral exists, then I am defining integral of f over the region D, bounded region D, which is same as integral double integral of f2 del over the bounded rectangular region R. So, that is how the definition is. Okay. So, I tried to explain in terms of pictorially. Okay. So, picture. So, integrations over non-rectangular region in the following pictures. So, what is your R? So, R is actually this one. If you look at this is your R regions. Okay. So, this is not a rectangular. Then what I am doing? So, now this is the R prime, right. So, I am having a big one R prime. So, an R prime is actually containing your region what is called R. So, now I have a rectangular region, and in the rectangular region you will have the notions of double integral. So, this is I tried to written, okay, this is the lower sum, that means it will give you some lower value or some lower approximation of your area or volume, and this upper sum, that means the it is bigger than your what is called the volume and area, that means this is the bigger one and this is the lower one, and this is lower sum or upper sum or lower integral upper integral, and whenever they becomes coincide, it becomes my function is what is called Riemann integral or Darboux integral. So, that is I tried to explain. So, inscribed parallelepiped and circumscribed parallelepiped, okay, and f is 0 on this region R prime minus R. Okay. So, that is kind of pictorially, because even if my domain is not bounded rectangular, in fact, I should say not rectangular, of course, it is bounded. So, if I have a bounded region, then what you get a little bigger rectangular region which is bounded, and perform your what is called double integral, and outside of course you have to perform the double integral of what? Of a newly defined function f two del, which is exactly equal to f as long as your point is coming from your domain D and outside it is 0. Then once the function newly defined function f two del is Riemann integral or double integral exists, which is exactly equal to the double integral over the domain D. Okay, so there is a small note what I have written: if D is bounded set, okay, so that means it is a bounded set in R2 with some arbitrary shape, that means I do not have any control on that shape, then computing the double or iterated integral you may find it difficult, right. So, like if I have a square region, bounded square, then of course the defining double integral or iterated integral very easy, because I know the kind of boundary and I can do that. So, however, if my D is like bounded, just bounded set or bounded domain, but it is like arbitrary shape, then it is very difficult to compute the double and iterated integral. However, couple of bounded region I will talk about in my next couple of slides. Even though the shape is little difficult, but still it has some pattern, okay, and you can easily perform the what is called your double integral or iterated integral. So, but of course those domains are specific, not like arbitrary. So, I have a specific bounded domain that I am denoting as a simple or elementary region, that I have written. We look for simple or elementary region or domain D, on which evaluations of the iterated integral become easier, that I will talk about. So, it is a very certain domain you will have there. It is not like what is called bounded rectangular domain, rather it is a nice domain which has some pattern, and in that domain you can calculate what is your iterated integral and double integral. So, those sort of couple of domains I will talk about, and then I will talk about the formula for calculating the iterated integral, and of course, if you have a Fubini's theorem, then the evaluations of double integral. But not like, again as I said, it is like not like bounded rectangular domain, but it is a bounded domain, but it is a different sort of domain, not rectangular. But even then, if the domain is nice, that I will talk about what are the domains I am going to talk about. If the domain has that kind of pattern, then you will be able to calculate your iterated integral, and by Fubini's theorem also you can calculate the what is called double integral. Okay. So, that is I have written simple and elementary regions in R2. Okay. So, like so simple and elementary integrals. Okay. So, let me just talk about one vertically simple region. In my next lecture I will talk about something more. So, what is that? So, this kind of region. So, this is a very nice region, right. Look, see, I have written vertically simple, type 1 and Y simple regions. Okay. So, what is that? So, region should be like that. So, this is the color. So, orange color is there. So, this is the region I have. So, I am saying that this is vertically simple. Vertically simple means what? You see. So, I have written. So, that means it is a region, of course, is sitting say subset of R2, but now it has a kind of some special properties. What? Now, x is running over the interval a to b. So, x is fixed. So, you have a fixed interval a to b in the x axis, this is fixed. However, y this time what will happen? It should varies from g1x to g2x. What is g1x? g1x is this is the boundary curve and this is the boundary curve g2x. So, y should lie between the curve, it's greater equal to g1x and lesser equal to g2x. So, earlier rectangular region means what? X is belongs to a to b and this is also c to d, right. If you remember, this is c and this is d. That means actually you are talking about the constant functions. g1x is equal to c and g2x is equal to d. That is the constant functions. Now, I remove that conditions. So, I am saying that x varies from a to b. So, that means left hand side is fixed a, right hand side is b fixed. But I am allowing my y left hand side, instead of the fixed, means instead of the rectangular region, bounded rectangular region, instead of the constant functions, I am allowing the function g1, which is a continuous functions on the interval a to b, and I am considering the right hand one, which is another curve, which is a continuous functions on the interval a to b. So, earlier you will have a constant functions. Now, this time I am replacing constant function by some continuous functions defined on the interval, closed interval a to b. If R has this kind of region, then I am saying it is vertically simple or type 1 region. For example, look this one, this is the color. So, that means what? So, x is varies from a to b, right? And what will y varies? So, this is y varies from g1x. So, that means y is here, g1x up to g2x. Okay. Look at here. So, this is x is varies from a to b. Now, y is varies from y. This is my g1x. Okay. This is my g1x. So, g1x to g2x. So, it starts. So, this is the one point. So, if your region is like that, then I will say that this is a vertically simple or type 1 region. But you have to be careful. So, I am keep x should varies from closed interval a to b, but y should varies from one continuous function g1x to g2x, where again I have written g1x and g2x are continuous function on the closed interval ab, along with the fact that g1x should be less or equal to g2x. That is also needed, otherwise cannot have this kind of things like this. It does not make any sense. So therefore, what I want that x should vary in the closed interval ab, however y varies from g1x to g2x, where g1 g2 are two continuous functions on the closed interval ab, with the fact that g1x is less or equal to g2x for all x in ab. If your domain is like that, then I will say that this is vertically simple. Okay. Then there is a notion of horizontally simple. Of course, you can now easily connect. Now, if it is vertically simple, that means I am keeping x in the closed interval ab and y varying from function of x to another function of x. So that means it is vertically simple. Then what is the type 2 or horizontally simple? Then you keep your y variable fixed and then varies x from function of y to another function of y. That exactly I am doing. So this is my C2D, and then I am varying my what is called x variable. So y is fixed. So this is C2D, y is fixed, and I am varying x. So from here to here, here to here. Similarly, this is my y is fixed. So this is y is fixed, y is fixed. Okay. Now I am varying x from here to here, from h1y to h2y, here from h1y to h2y. If this is the case, this is called horizontally simple or type 2 region or x simple regions. Again, look, so this is the xy belongs to R2, where y is running from C to D, y is fixed, right? C less or equal to y less or equal to D. But however, your x varies from h1 y less or equal to x less or equal to h2 y, where h1, h2 are two continuous functions on the closed interval C to D, with the fact that h1 y is less or equal to h2 y. Okay, so I think I should stop here. So this is, I have two simple regions I have talked about. One is vertically simple, another is horizontally simple. Then there is a domain what is called both type 1 and type 2, like both vertically simple and horizontally simple. Then I will talk about some non-simple region. Now the question is, if I have those kind of regions, can I calculate my double integral or iterated integral? I think in my next lecture I will talk about that. I think I should stop here. Thank you.